In today's lesson, we're going to be talking about independent versus dependent variables, and also we're going to hit on function notation. So first of all, the independent variable is also called the input of a function. This is the x variable, whereas the dependent variable is the output of the function, the y variable. And the value of the dependent variable depends on the value of the independent. So we're going to take a look at some examples where we're going to be determining independent versus dependent variables. This first example says, during the winter, more electricity is used when the outside temperature goes down and less when the temperature outside goes up. The blank depends on the blank. So first of all, let's pick out our variables. It says during the winter, more electricity is used. So electricity is one of the variables, the electricity usage. And then the other variable is the temperature. And we have to decide which one depends on the other. So in this scenario, the electricity usage depends on the temperature outside. So that means the independent variable is the temperature, and the electricity usage is the dependent, because the electricity usage depends on the temperature outside. So again, that's the dependent variable. Here's the next example. It says the cost of shipping a package is based on its weight. So the blank depends on the blank. Again, we have to identify the variables. So cost is one of the variables that is varying in that scenario. And then the weight is the other. So we have to determine, should we fill that in the cost depends on the weight, or the weight depends on the cost. So the cost depends on the weight. So since the cost depends, the cost is the dependent variable and the weight is the independent variable. So when we want to write an equation to represent a particular scenario, it's important that we identify the independent variable and the dependent variable. So here's an example of a function that we are going to write in function notation. And then we're going to determine the cost for 7 hours of babysitting. So it says Amanda babysits and charges $5 per hour. So we need to decide between time and charge, which one would be the independent variable and which one would be the dependent variable. So in this case, the charge is going to depend on the time spent or the hours spent babysitting. So in this case, the time is the independent, and the dependent variable would be the charge. Now, when we write this in function notation, it might be a good idea for us to use variables other than x and y. So let's say, for instance, we wanted to use t for time, and let's say c for charge. So we would say the charge for a particular amount of time is equal to $5 per means times. So $5 times the amount of hours spent. So the charge at time t is equal to 5 times t. That is in function notation. It means the same as y equals 5x. Or if I use the variables that I've picked there, c equals 5t. All three of those functions mean the same thing. They're just in different forms. We are going to focus on this function notation as the preferred method right now. Okay, so if we want to know how much she's going to charge for 7 hours of babysitting, I would say the charge at 7 hours is equal to 5 times 7. Or the charge for 7 hours is $35. Okay, here's the next example. The admission fee at a carnival is $9 and each ride costs $1.75. So we have the fee, that's one of the variables. And then we have the idea that we're going to have a cost per ride. So the number of rides would be the second variable. So I'm going to say F is going to equal the fee, and R is going to equal the number of rides. Again, I'd want to kind of think about which one's the independent variable and which one's the dependent variable. So the fee is going to depend on the number of rides that we take. So the fee is the dependent variable. And the number of rides is the independent variable. So if I wanted to use X and Y for my variables, the independent is always X and the dependent is always Y. But again, I'm using function notation for this one, so I'm going to stick with F and R. F is standing for fee and R is standing for the number of rides. We see that it's going to cost somebody $9 to get in, and they're spending $1.75 per ride. So thinking about translating that into a function, I would say the fee for a particular number of rides is equal to $9 plus $1.75 per ride, which means times the number of rides. Okay, and to find a particular fee, it asks us at the bottom, how much does it cost if you go to the carnival and ride on 12 rides? So I want the fee for 12 rides. That's going to equal that $9 plus $1.75 times 12 rides. All right, doing that math, the fee for 12 rides is going to be $9 plus $1.75 times 12 is $21. And if I add those two together, we get $30. So the fee to ride 12 rides would be $30. Okay, hopefully we're feeling comfortable with the whole idea of independent versus dependent events and writing, again, translating into equations. The second part of this note's just going to refresh function notation and do a little bit more practice with function notation. So we have three functions that we're going to be using. F of x is equal to 7x minus 5. G of x is equal to x squared plus 6. And h of x is equal to x cubed minus 1. So for the first one, it asks us to use f's function and evaluate when the input is 2. So if we look at function notation for the function f of x is equal to 7 times x minus 5. The input, again, is 2. So I'm going to enter the 2 where the x is in that function. So 7 times the value of x, which we said was 2, minus 5. So we're just substituting the 2 in for x. 7 times 2 is 14, and 14 minus 5 gives us 9. right, we're going to go ahead and do the same thing, but now with G's function, and the input is -3. So again, that's asking us to substitute -3 in for x. So looking at G's function, g of x is equal to x squared plus 6. If we plug in the -3 for x, that would say -3 squared plus 6. Now be careful when you evaluate this because of the signs. -3 squared, a negative times a negative makes a positive. So we would get 9, positive 9, plus 6, which is 15. We're going to evaluate h at -2. So that's asking us to put -2 into h's function. H says x cubed minus 1. So if we plug in -2 in for x, that would be -2 cubed minus 1. Again, be careful of signs here. A negative times a negative makes a positive, but then we're multiplying it by another negative. So that's going to be negative, and then whatever we get there for 2 cubed, which 2 times 2 is 4, 4 times 2 is 8. So it's -8 minus 1. We get -9. So those 3 examples all gave us x values or inputs of the function and was asking us to find the outputs. These next 2 examples are reversing the process. So instead of giving us the input, we do not know the input, that we're saying whatever x is the input, but the output is supposed to be 9. So using f's function, when we put some number in for x, we're supposed to get 9 as the output. So I do not know what I'm substituting in for x, so I'm just going to use the 7x minus 5 because that's f's function, but I know that the output is supposed to be 9. We've talked about how to solve these equations in the last couple weeks, so let's add 5 to both sides. We get 7x is equal to 14, and divide both sides by 7. We get x equals 2. So guys, if you notice, we were asked to put an x value, an input value of 2 in to the function in number 1. We got 9 out as the output. This was the exact opposite of that. It's asking us to put 9 as the output and find the input. So questions 1 and 4 are actually the same question, just asked for different things, one for the input and one for the output. Taking a look at number 5, f of some number is equal to -26. They're asking us to find y. Again, we do not know the input of the function, so we do not know what value is being substituted in for x. But we know the output is -26. So I'm going to say 7y this time because, again, it's using the variable y instead of x there, minus 5. The output is supposed to be -26. So the input is what's going in for x. In this case, y is going in for x. And this is the output, -26. All right, let's solve that equation. So add 5 to both sides. We get 7y is equal to -21. And divide both sides by 7. And we get y equals -3. So when you put -3 in for x into f's function, we should get out -26. So you could always check yourself, plug that -3 in for x. 7 times -3, that gives me -21, minus 5. -21 minus 5 gives me that -26 that we're supposed to get for the output. That's perfect. Okay, this slide is still asking us to evaluate functions, giving us inputs, and we're supposed to find the outputs. However, these are a little bit more advanced function notation questions. So this first one is asking us to evaluate f of 9 minus g of 2. So we're using both f's function and g's function here. The first part asks us to put in 9 into f's function. So 9 is the input. So if I look at f's function, it says 7 times x. Well, we're putting 9 in for x minus 5. And we're subtracting off g of 2. So 2 is the input, but we're plugging it in g's function. So g's function says we take x, in this case 2, and square it and add 6. Again, we're subtracting those two values. So we're going to find f of 9. 7 times 9 is 63. 63 minus 5 is 58. And we're subtracting off g's function when the input is 2. So 2 squared is 4, and 4 plus 6 is 10. We're subtracting those two values, so 58 minus 10 gives me 48 for number 1. I'm going to go ahead and erase these as we go through the different problems, since there's not a whole lot of room there. So taking a look at number 2, we see we're evaluating h of 0. So I'm looking at h's function, and I'm inputting 0 into that function. So h's function says x cubed, or in this case 0 cubed, minus 1. And we're adding on g of 4. 4 is the input. We're inputting 4 into g's function. So looking up at the top, x squared plus 6 is g's function. If we put 4 in for x, 4 squared plus 6. All right, let's go ahead and evaluate. 0 to the third power, that means 0 times 0 times 0, which is still 0, minus 1, that gives me negative 1. And we're adding that to 4 squared. 4 times 4 is 16. 16 plus 6 makes 22. Again, we're adding those two values together, so negative 1 plus 22 gives me 21. All right, number 3, we're taking f of 2 and multiplying it by g of 1. So plugging 2 as the input into f's function would say 7 times 2 minus 5. We're multiplying that by g's function evaluated with an input of 1. So that would say 1 squared plus 6. Okay, 7 times 2, that's 14. 14 minus 5 gives us 9. We are multiplying that by 1 squared is 1, plus 6 is 7. So 9 times 7 is 63. All right, number 4 is something called composite functions. It's kind of like order of operations. We're going to do what's inside the parentheses first, and then that's going to leave us with another function that we have to evaluate. So I'm going to write this whole thing over here, f of g of 3, but we need to do the inside the parentheses first. So we need to evaluate g of 3. 3 is the input into g's function. So g's function says x squared plus 6. If we plug 3 in for x, that would say 3 squared plus 6. And I'm bringing down the f is just tagging along for the ride. Let's go ahead and simplify inside parentheses. 3 squared, 3 times 3 is 9. And 9 plus 6 is 15. So now we see that we're evaluating f with an input of 15. So f of 15. If we plug 15 in for x into f's function, that would say 7 times 15 minus 5. Okay, let's grab those calculators. This one's a large value. Okay, 7 times 15 is 105 minus 5 gives us a final answer of 100. So to recap, when you have composite functions, which composite just means you have more than one function that you're evaluating, you always work from the inside out. So do what's in parentheses first. For number 4, we evaluated g's function with an input of 3. When we evaluated that, we got 15. And then we evaluated f's function at 15. So that was the function that was on the outside, and we evaluated it for the simplified value that we got when we simplified g's function at 3 there. Okay, last example on this particular slide is another composite function. Again, we're going to work from the inside out. So I'm going to write the whole thing, g of h of -1. But again, I'm evaluating the inside of that function first. So I need to find the h's function when it has an input of -1. So if we plug -1 in for x, again, into h's function, it says x cubed minus 1. So if we plug -1 in for x, -1 cubed minus 1. I'm going to bring that g down to tag along for the ride. All right, let's evaluate h at -1. So -1 cubed, that means -1 times -1 times -1. That's still -1. Minus 1. -1 minus 1 gives us -2. So now we're evaluating g's function when the input is -2. So I'm going to plug -2 into g's function, which says x squared plus 6. If I plug -2 in for x, that would say -2 squared plus 6. -2 times -2, that gives me +4, and +4 plus 6 gives me a final answer of 10. So we have first evaluated h at -1, and then we evaluated g at -2. So those last two examples were two examples of composite functions. Okay, our last slide of our notes today is just asking us to combine like terms when we are simplifying functions with varying operations, like addition, subtraction, multiplication, composite. So this first one is asking us to add f of x plus g of x. So first of all, f of x's function says 7x minus 5. And it's asking me to add on g of x's function, which g of x says x squared plus 6. So I'm going to just check for like terms here, guys. If I look, there's not a whole lot that's like. I have two constants that I could combine, -5 and +6. But the x squared is different than the 7x and is different from the constants. So I'm just going to bring everything down that does not simplify. X squared has the highest degree, so I'm going to bring that down first. The +7x would be next. And if I combine the constants, -5 plus 6 would give me +1. So this is the final simplified expression for number 1. Taking a look at number 2, it's asking me to take h of x and subtract off f of x. Now we do need to be careful with signs here. H of x is x cubed minus 1, and we're subtracting off f of x, 7x minus 5. To get rid of those parentheses, you can almost think about that as distributing the negative sign, or distributing a -1. So -1 times 7x, that would give me -7x. And -1 times -5, that would be +5. I'm going to bring down the x cubed and the -1, and again check for like terms. I have two constants that I could again combine. So x cubed, there's nothing like that. The next highest degree is -7x. And if I combine the constants, -1 plus 5 would give me +4. Okay, these next two are composite functions. These composite functions, again, I want to work from the inside out. So first it says f of g of x. So I need to figure out, well, what does g of x say? G of x is equal to x squared plus 6. We don't have an input that we're substituting in for x, so we're just going to leave it as that expression, x squared plus 6. The f is going to tag along for the ride, so I'm just going to pull that straight down. This expression here is asking me to plug x squared plus 6 as the input into f's function. This is a little tricky, guys. So f's function says we take 7 times the value of the input. Well, our input is this whole expression, x squared plus 6. And then -5 is, again, still part of f's function. So we plugged this x squared plus 6, that whole expression, in for where x was in f's function. So we have 7 times the quantity, x squared plus 6, and then -5. We can simplify this a little bit by distributing that 7. So 7 times x squared is 7x squared. 7 times 6 is +42. And I'm just bringing down that -5. Again, we can simplify a little bit more because those two constants. So 7x squared, and if we add the 42 minus 5, that would give me +37. So this would be the final simplified form. Excuse me. Okay, the next example is kind of similar to that. Excuse me, but it's asking me g of f of x. So again, we're going to work from the inside out. First, I have to plug in f of x's function. So f of x says 7x minus 5. The g gets dropped down. It's tagging along for the ride. So this is asking me to evaluate g's function when the input is 7x minus 5. So this whole expression needs to go into x, or substituted in for x, into g's function. So that expression, 7x minus 5, that whole quantity is being squared plus 6. We're going to be talking about how to simplify the expression a little bit later in the course. So for right now, we're going to leave that as our final answer. Okay, our last example says f of h of x. So it's a composite function there, but then we're adding 6 to that. So again, we start from the inside, parentheses first. We're plugging in h's function when the input is x. So h's function says x cubed minus 1. And the f is brought down. I'm also going to bring down the plus 6 so we don't forget about it. Now we're evaluating f's function when the input is x cubed minus 1. So that x cubed minus 1 is going into x for f's function. So that would say 7 times our input of x cubed minus 1 minus 5. And then I'm bringing down the plus 6, dropping that straight down. Again, we need to simplify and combine like terms. So distributing the 7, we get 7x cubed minus 7, bringing down the minus 5 and the plus 6. The only thing that we can combine here are all of those constants. So negative 7 minus 5, that gives me negative 12. And negative 12 plus 6, that gives me negative 6. So 7x cubed minus 6 would be our final answer. Now, I know, guys, those composite functions can be a little complicated at first. We're going to be doing more practice with those couple different places throughout the course. So if you're struggling with those right now, don't worry too much about it, but feel free to ask questions if you have them.